Welcome to the second lesson on significant figures. In this lesson, as we had said earlier, as I promised, we will go through some selected problems from the eWorkbook that I've also shared in this video under the comment section. Under the comment section, you'll find I've shared the eWorkbook from where these questions are coming from. Okay? So this is going to be a very short video because I've selected just a number of the questions to be looked at. Okay, so let's begin. All right, the first question comes from I think this is going to be on page 3, and this is the first level of questioning, level A, and we are looking at question number 2. So if you go to question number 2, this is what you will see. You have the Verrazano-Narrows Bridge in New York. We are told that its main span length, so this bridge has got several spans or several sections, and the main one has a length of 1,289.4 meters. Okay, the question is, which of the following would these groups of New York residents report as the length of the bridge? All right, so the length that an individual would report if they were asked to say what the length is depends on, you know, how many digits are important to them. Okay, so we have a group of individuals here, and we are supposed to think about what one of the New Yorkers is a regular tourist, another one is a structural engineer, there is a taxi driver, and there is a marathon runner. So if we ask these people what the length of this bridge is, what value, what number are they likely to give and why? All right, so this question appeared in level A, and take a few seconds and think about what answer you would give here. So a regular tourist is generally not interested in so many number of digits. Okay, so for such a person, they may look by just looking by measure of eye, the most likely answer they are going to give us is that the length of that bridge is about 1,000. They'll say it's about 1,000 or about 1 kilometer long. Right, so that's enough for a regular tourist. Okay. When it comes to a structural engineer, this fellow needs more detail, because structural engineers, a small margin of error can usually cause something like a bridge to collapse, so they want exact figures, right? If they were going to map this, or if we're going to use these same measurements to build another bridge elsewhere, then they want exact figures, and so a structural engineer is likely to give the figure to 5 significant figures, which is the last reading there. So we are saying the regular tourist is likely to just say, oh, the distance is about 1 kilometer. That means 1 significant figure is sufficient, is appropriate for a regular tourist, while for a structural engineer, it's likely that they're going to require all the digits in the measurement. Okay, so this engineer would probably say 1,289.4 meters as the length of the bridge. He's probably going to go and dig into the papers that were involved in the construction of the bridge and dig out the exact figure. All right, what about a taxi driver? A taxi driver needs enough distance, but they are likely to want to round off so that you can pay them more. So therefore, given 1,289 and 1,300, a taxi driver is probably not going to care so much about that figure, and they'd rather give a figure higher than the actual length. So we would expect a taxi driver to give a figure of 1,300 meters, which is a figure given to 2 significant figures. All right, the number is given to 2 significant figures. A marathon runner will want an exact distance, but a person running a marathon distance is probably not so interested in the 0.4. They want to know the exact figure, but once again, the 0.4 there means 40 centimeters, which is about that length there. They're probably not going to be so interested in that. So we would say we'd probably pick 1,289 as the distance that a marathon runner is going to to say. We can argue that a marathon runner may also say 1300, but you know, any of those answers would suffice. I guess what we are thinking about here is reasoning as to what number is important to who, depending on the relevance of the information. Okay, so that was that question. Let's go to the next question. The next question. The next question is on page 4, level B, tasks, and I have picked here question number 1. How many significant figures are each of the following numbers? So we want to know the number of significant figures on these numbers. I want to remind you here of the slogan we've been using, and that is whole is right. So if we have a whole number, then we count significant figures starting from the right, and therefore if it is not a whole number, we will start from the left. Okay, so whole means we start from the right, otherwise we start from the left. Okay, so here are some values. I'm just going to put this, I think there are 3 of them. I will put the space where to answer these questions here. And so if we look at the first one there, this is not a whole number, so we do not start from the right, we start from the left. So because it is not a whole number, it's a decimal number, we start from the left, and we start counting from the first non-zero digit and then count everything. So the first non-zero digit there is 1, and so after 1 we count 1 and everything else that comes after. And if you check that, then we should be able to see that this figure here is to 4 significant figures. Okay, so 0.01011 is to 4 significant figures. All right, the next one is 543, and as you can see, this is a whole number. Since it is a whole number, we start from the right. Whole is right. That means we'll always start from the right if it's a whole number. So we start from the right and count all digits, starting with the first non-zero digit, and that means we count all the 3, which means this is 3 significant figures. Okay, the last one there is not a whole number. There is a 0.01. That means we start counting from the left. All right, and we count everything starting from the first non-zero digit, and 3 is a non-zero digit, so 3, 6, 0, 0, 0, 1, all of them are counted. And if you check that, you should see that this figure or this number is to 6. This is to 6 significant figures, like that. And that's how we can check the number of significant figures on any given number. Please look at the rest and write down the number of significant figures that those numbers are. Okay, we'll move to the next one. And so through these questions on significant figures, your job really is to remember this slogan here, so that you use 2 rules for significant figures as opposed to the usual 5 rules in the textbooks. Okay, let's move to the next question. The next question is still on page 4. We are still on level B, so this is basically the same exercise, and now we are looking at question number 2. All right, and it says state the number of significant figures of the reading on the instrument. Now I've picked this particular instrument intentionally because I know that you do not know how to read, to record, or to read that measurement. So this is a micrometer depth gauge. It is used to measure the depth of a groove, such as what you would use for measuring the groove on a car tire, right? So the length of that groove, that depth gauge there, is what this thing records. Okay, Let's see how to answer this question. We want to know how many significant figures the reading has. To do that, first of all, we need to be able to measure that. Once we can read the value there, then we will be able to see how many significant figures it is, okay? So first of all, let's talk about this. I'm going to blow out that area where we have to take the reading. This is about that area there. Okay, so that's the area we are interested in. We blow it up so we can see it more clearly. Now, this section here is called the sleeve, just like the sleeve of a shirt. So this section here is the sleeve, and the graduations there, this is called the sleeve scale, okay? And that other one there, the upper one, is called the thimble. So this thing here is called a thimble, and the readings on the thimble are the thimble scale. So when we want to take a reading, first of all, we go to the sleeve and we record. So if you look at the numbers here, there is a 0 somewhere up there. So 0, then there is a 5, then there is a 10, then there is 15. So you can see coming from 0, we have gone until we are at, so that is 10. So before that, since between 10 and 15, this is divided into 5 equal parts, and on this side, the readings on that side are referring to the 0.5. So we have, for example, 10, and then next to it down there is 10.5. Then we have 11 and 11.5, like that. And so on this side is 10 up to 15. That is divided into 5 equal parts. So each bit is 1 millimeter, okay? And so coming from the top where 0 is, we can see that we have just gone past 7, but we have not reached 7.5, which is that mark right there, right? So we have not got to 7.5. So our reading lies between 7 and 7.5. So we are going to write that our reading is just over 7. So we'll write 7.0 to represent our reading. So the reading as given by the sleeve is lying between 7 and 7.5, so we will write 7.0 like that, and it is 7.0 millimeters. Okay, now we go to the thimble reading, and you can see the thimble, the readings start from 0 and go all the way 100 of them. So each tiny split here, split here refers to 100th of a millimeter. Okay, and so what reading that you see there, so the line here helps us see the reading there, and if you check that carefully, it is at 14. So there is 10 at the top here, this is 10, and so that is 15. So if you check that datum line, that black line going up, it is pointing exactly at 14. So therefore that reading there is 14th of 100. In other words, 14 out of 100 millimeters, or 0.14. So we can say the reading there is 14. So the thimble reading is 14, and we read that as 14 out of 100, or 0.14 millimeters. And so that tells me that the depth as being recorded by that instrument must be 7 plus 0.14, and that is 7.14 millimeters. This is how we read on a micrometer screw gauge, or in this case, micrometer depth gauge. So our reading, therefore, the instrument reading is therefore 7.14 millimeters. And now knowing the reading, now we can talk about how many significant figures that is. Because this is a decimal number, we cannot start from the right, from using our slogan, so we must start from the left, and either way, when you count that, you should see that that is 3 significant figures directly. Okay, so our answer there is 3 significant figures. I've left out the other instruments because the readings are clearly indicated on the instrument, and so you should easily be able to, tell what the reading is and then count the number of significant figures each reading is indicating. Okay, thank you. Let's move on to the next question. This is now on page 7, and we are looking at level C questions, In particular, we are looking at question 6b. And what does question 6b say? It says to evaluate the following: 9.55 times 10 power 5 plus 31 times 10 power 4 minus 0.063 times 10 power 6. Okay, so we are going to evaluate that. We can see that we are actually adding or subtracting the numbers. When you subtract or add numbers, we are interested in the number of decimal places. So we can see that this is 2 decimal places here. This is right now no decimal place, and this is 0.63, which is 3 decimal places. But before we even go there, if we are going to add or subtract numbers expressed like this, we must first ensure that they share the same power of 10. Okay, so this is 10 power 5, this is 10 power 4, this is 10 power 6. So before we proceed, we must manipulate them to have the same power. We can choose that we want them to be to power 4, or we want them to be to power 5, or we want all of them to be to the power of 6. So for this example, I've chosen to the power of 5. But the other thing, of course, we could do when the powers are not so big like this, sometimes you have powers like 28 or power 21 or power negative 19, as the example I gave earlier in the first video. In that case, it's not possible to do what I'm about to do. But when the numbers are small, like 5, 4, and 6 like this, we can choose to write this as 10, that would be 100,000, and so multiply this by 100,000, and we would get 95500. We change them to their real values. This would be 31 and 4 zeros, so 31 and 4 zeros, so that would be 310000, like that. Okay, and the next one there, we are multiplying by 10 power 6, so that would be 63 and 3 zeros. 63, so 6, 3, and 3 zeros. Okay, the only thing is that the first 2 are being added, and then we will subtract. So these first 2 are added, and then we are going to subtract the last one. So when we add this, what do we get? That is going to be a 0, 0, 0, and 0. There are 4 zeros. Actually, there is a 5 there, so I'll remove this and put a 5. Okay, and then that would be a 6, and this would be 12, like that. So that would be when we add those 2, and then we can subtract 63,000, and if we do that, if we subtract, we get a 0 there, a 0 there, a 0 there. 5 minus 3 would be a 2, 6 minus 6 would be a 0, and 1, 2, like that. So this would be our reading. And so if the answer is required in the correct number of, because we are adding this, if we wanted to write this in scientific notation, we would say we have an answer of 1.202, and we say times 10 to the power of 6, and that would be our value. Okay, because we are adding and there is no decimal number there, we would leave our answer like that. Okay, in this case, we are allowed even to reduce this to 2 significant figures, provided that we have done this calculation like that. All right. The alternative of doing this when powers are very large, so we are going to use another method here, but assuming that those powers are large, what do we do? All right, so the other thing we can do is to, like I said, we can choose that we're going to have a uniform power of 10. So for this purpose, I'm going to choose power 5, for example. So first express the numbers to a common power of 10. So for our purpose, I have chosen 10 power 5, but we could have taken 10 power 4, and we could have taken 10 power 6. It doesn't really matter. All right, so we start with the first one. The first one is already under 10 power 5, so it's done, so we don't have to do anything with it. But the second one is power 4, so if we're going to turn it into a power 5, what do we do? So I've just shown the steps, but you don't really have to. You can change it to a power 5 directly from here. multiplying by 10 power 1 here, and then dividing by or multiplying by 10 power 1 and 10 power negative 1. 10 power negative 1 moves the decimal point back. So you can do that, but let's go in steps. So what we do, we have 31 times 10 power 4. Then I'm going to concentrate on 31. I'm going to express 31 in scientific notation. So 31 then becomes 3.1 times 10 power 1. Okay? And then after that, now we can multiply by 10 power 5. Okay, 10 power 4. And if I combine this and that using our laws of exponents, I end up with 3.1 times 10 power 5 as I wanted. Okay? So that's the case. All right. Next, I have, the second number is now 10 power 5. It's now expressed with 10 to the power of 5. All right. Now we go to the last one. The last number there, 0.063 times 10 power 6. What I'm looking for is a 10 power 5. So I need to subtract a 10 power 1 there. All right. So to do that, I have to write the 0.063. If I'm going to have a 10 power negative 1, so we need 10 power negative 1 to reduce that to power 5. So if I'm going to get a 10 power negative 1, then I have to move this decimal point back one step. So I'm going to write this not in scientific notation, but as 0.63 times 10 power negative 1. So that number in bracket can be expressed like this. Notice this is not scientific notation, and the reason is because the first number, A, is not lying between 1 and 10. If you remember the rules we discussed in video number 4. Okay, so this is not scientific notation. I've done it conveniently so that I get a 10 power negative 1, which when I multiply by 10 power 6 will give me 10 power 5. So now I can put my 10 power 6 there. So the yellow bit is just the 0.063, and now I multiply by 10 power 6 there, and you can see we will end up with 0.63 times 10 to the power of 5. So now I have all my numbers expressed as a multiple with a multiple of 10 to the power of 5. Okay? Once I've done that, now I can add them as required and subtract as required. So I'm going to need to add, I only need to concentrate on the 9.55, on the 3.1, and on the 0.63. Remember, these two are being added while this one is being subtracted. So I can now write, I will pick the 9.55, I'll put it in bracket there, and I'm going to add the 3.1. Okay, so temporarily I will leave out the 10.5, the 10 power 5. Okay, so 9.55, we need to add 3.1 there, and then we need to subtract the 0.63. Okay, and into bracket, and now I can multiply by 10 to the power of 5. Okay, so this is like, you could think of 10 power 5 as x. So 9.55x plus 3.1x minus 0.63x. So if you add all of them, then you will have just 1x, right? So it will be 9.55x plus 3.1x. Whatever you'll get will be x, all right? So that's why we have just one 10 power 5 there. Treat the 10 power 5 as though it was an x, some unknown. All right, so when I add that and subtract, I get a total of 12.02. Try it out on your calculator. I get that bracket there gives me 12.02, and now I can multiply by 10 to the power of 5. And I want to express my number in scientific notation. Okay, so this is not scientific notation because 12.02 is beyond 10. For it to be in scientific notation, the number that we write here has to lie between 1 and 10. So because of that, I have to change that 12.02, we have to turn it into a number that lies between 1 and 10. So I'm going to express that bit 12.02 as 1.2, scientific notation, 1.202 times 10 to the power of 1. And then I can now multiply by 10 to the power of 5. Okay, like that. And then we can combine the 10 power 1 and the 10 power 5 using the laws of exponent. That means the 1 and the 5 add up. and I end up with 1.202 times 10 to the power of 6, which I can now reduce. See, now I'm looking here, and I'm saying this is to, this one here is to 2 decimal places. This one is to 1 decimal place. Remember, all of them are power 5. So this is 2 decimal places. This is 1 decimal place. This is 2 decimal places. So because we are adding and subtracting, we should be considering decimal places, and we take the least number of decimal places there. And so our answer is going to be, we're going to have to reduce our 1.202 to just 1 decimal place, and that gives us 1.2 times 10 to the power of 6. And that is the answer to this question. Okay? You can try the other question on the same page that looks like this and see if you come up with the right answer. Of course, don't forget to ask me if any of the questions become confusing. All right, let's look at the next question. All right, this was page 7, and now we are in level C questions. And in particular, this one was question number 7. The average speed of molecules in air, so these are molecules in air. The average speed of molecules in air depend on the temperature of the surrounding. Those who are in the physics class, we are already discussing the behavior of molecules with temperature. How does temperature affect the behavior of molecules? We know that as you increase the temperature of a gas, the molecules inside move faster. If it is a solid, then the molecules vibrate with a higher frequency, and so on. So if this is a gas, the speed with which the molecules move depend on the temperature. And so we are told that at 25 degrees Celsius, we pick 5 out of the molecules. We pick 5 of them at random, and it is observed that they move at the various speeds. Okay, so one molecule is moving at 482.1 meters per second. Another one is 522.356 meters per second, and so on. So these are the speeds of 5 molecules randomly selected. The question is to calculate the average speed of the oxygen molecule at 25 degrees Celsius. So we can find the average of these and use that to represent all molecules of oxygen at 25 degrees Celsius. So what we're going to do is to just, if we're going to find the average, we just add all of them and divide by the number that they are, which is 5. Okay, now we know when we add numbers, we need to consider their decimal places when we want to find the answer, the number of decimal places in the answer. Okay, so that's what we are going to do. So as we are adding numbers, our answer should not have a decimal. Can you think of why our answer will not have a decimal? Well, you can pause the video and think about why the answer we get should not have a decimal point. It should not be point something. Well, the answer is that because we are adding, our answer must have the least number of decimal places as those possessed by the quantities that we are adding. All right? So we know that that one there is to 1, the first one there is to 1 decimal place, the second one is to 3 decimal places, the third one is to 0 decimal place, there is no decimal there, the fourth one is to 1 decimal place, and the fifth one is to 2 decimal places. All right, and so our answer must have the smallest of these. So it has to be to 0 decimal place. That's where our answer will not have any decimal place. So our answer must be to 0 decimal places. So the next thing we have to do is just to add them. I've done that on my calculator. Please check by doing the same addition on your calculator. And so what I find is that the average is going to be V is, so the numerator there is the sum of all those velocities. Please check that that is the answer. And then we divide by 5 because we have 5 molecules. You know how to find average. And when I do that calculation, I get 478.0772 meters per second. So this is the average velocity or the average speed of an oxygen molecule in space, okay, at 25 degrees Celsius. Of course, if I increase that temperature to, say, 30, then that average speed is going to increase because the molecules gain the energy and move faster, okay? Now we have the value of the average velocity or the average speed, but we need to give that to the correct number of decimal places. Now, as we have seen, the lowest number of decimal places is 0 there. So our answer has to be to 0 decimal places, and therefore our value for the average speed has to be 478 meters per second. That is the final answer. Okay, I hope this makes sense. Let's look at the next question, possibly the last. Let's see. This one. This one is on page 8, and now we are looking at level D questions. It is question number 2. It is not the last one. So we are given a road sign which says no entry. So this road sign here implies you must not go into that region or into that area or that zone. Okay, and in the question we are given the dimensions of this road sign. We are told that the diameter of the road sign, the circular part, is 199.82 millimeters. The dimensions are in millimeters. Okay, the length of that white rectangle part is 141.35 millimeters, and the width of that rectangular part is 39.98 millimeters. The question is for us to find the area that is shaded in red. How do we find the area shaded in red? Of course, we are just not interested in finding the area, but giving our answer to the correct number of decimal places or correct number of significant figures, if any. Okay? So the first thing, of course, we have to do, we are going to ignore the outer white line. Okay? So ignore that to make the work easier. So if we're going to find the area of the area shaded in red, we need to find the total area of the circle, the circular part, and then we need to find the area of the rectangular section, and then we are going to take the area of the circle and subtract the area of the rectangular section to give us the area that is shaded in red. Okay, so the question is express the diameter. So there's a part A and there's a part B. Part A says express the diameter of the traffic sign, part 1, to the nearest unit. That means to the nearest 1. In this case it's millimeter, so that to the nearest 1 millimeter. Okay, so the point 8 there, is it closer to 1 millimeter or closer to 0 millimeter? Well, it is closer to 1 millimeter, so we have to round up, and if we round up, this goes to 200. So to the nearest unit, to the nearest 1 millimeter, our reading of 199.82 has to climb to 200 millimeters. Okay, to the nearest unit means to the nearest millimeter. Okay, if this was meters, then we would say we give our answer in meters. All right, part 2, to one significant figure. Give your answer to one significant figure. Well, 199.82, if we were to write this to one significant figure, we know it's going to be the same as that. Okay, so that if we round it off, the 8 goes in there and turns this into a 0, which in turn turns that into a 0, which turns that into a 2. And so our answer is going to be 200 millimeters to one significant figure. Okay? Part B of the question says to find the area of the area shaded in red, giving your answer to the nearest, to the correct number of digits and in scientific notation. Okay, so we are going to multiply stuff and then we are going to subtract stuff. Right, so while we multiply, we follow the rule for significant figures, and when we add or subtract, we follow the rules for decimal places. So let's start then. The area, we start by looking for the area of the circular part. The area of a circle is pi r squared. So for a circle area, I'll write this here, area is pi times the radius squared. Okay, we can also write it as pi radius. R radius is the same as diameter divided by 2. So we can say r instead of r squared, I can put diameter divided by 2 and then say squared, like that. Okay, so that's one way of finding the area of the circle. I'll remove this now. Okay, so we're going to use that rule there. And so our diameter is 199.82. We need to divide that by 2, like that, right? So therefore, area of the circle is going to be pi times the radius divided by 2, everything squared. And if you work that out in a calculator, you find 300. Actually, you find a decimal number, very, very long decimal number. But because the number 199.82 is to 5 significant figures, when we square it, that means multiply by itself. We are multiplying. Our answer has to be to 5 significant figures. And so our answer there, whatever decimal numbers you get, you have to reduce it to 5 significant figures. And so it is 31,359 square millimeters. That's the area of the circular, the whole circle. Okay? Now we need to find, I'm going to put that somewhere up there. Let's move that there. Okay. And then now I need to calculate the area of the white rectangle there. So the area of a rectangle is of course length times width. I don't have to write that down. So the length is 141.35 and the width is 39.98. So we need to multiply those two. Okay, whatever we get is going to be in square millimeters. I have done that calculation. Now, this is 4 significant figures and this is 5 significant figures. So our answer has to be to 4 significant figures. Okay, and so I found that there were decimal places, but I've reduced it to 4 significant figures. Okay, because that is the smaller number of significant figures. So that is the area of the white section. So now what is left for us to do is to subtract, okay? Take the area of the circle, subtract the area of the white section, and that leaves me with the area of the region that is shaded in red. So I'll put that value there, area of the rectangle, and so my task now, area that is shaded in red, is the area of the circle, subtract the area of that white rectangle there. And when I subtract, I get 25,708 millimeters. Okay. Now our answer, the values that we are subtracting are not decimals. There are no decimals on them. So my answer should not have any decimal on it. Okay. So this is the answer for the area shaded in red. But we are also asked to give the value to the correct scientific notation. Okay. So how do we write 25,708 in scientific notation? Well, the number we start, so it has to be in the notation A. So this is our N, and N needs to be, so N needs to be expressed as A multiplied by 10 to the power of K. A must have the same digits as this and in the same order, except my value of A must lie between 1 and 10. So think about a number that lies between 1 and 10, which has the same digits 2, 5, 7, 0, 8 in that order. And if you check carefully, that number must be 2.5708. Okay, and now we say times 10 to the power of K. The value of K is what you get. So the number we are converting is 25708. That's what we are converting. Now, if you look at 25708, the number itself, the decimal for this number is somewhere just after 8. That's where the decimal point is. So our decimal point is somewhere there. And the question is, how many decimal places have I moved it to bring it between 2 and 5? And if you check that carefully, we moved it from there 1, 2, 3, 4. So we've moved it 4 places in order to make this number. For that reason, this power here is 4. And because the number we are converting to scientific notation, because that number is greater than 10, our value of K here, the 4, is going to be positive as it is. If this number was less than 1, then this would have to be -4, like that, okay? And so this becomes the value expressed in scientific notation. Let me put that nicely. Okay, so let's put this more neatly. So in scientific notation then, this becomes 2.5708 multiplied by 10 to the power of 4, like that. That has to be our final answer for the area of the region that is shaded in red. I hope you are understanding this. Let's go to the next question, possibly the last one, I believe. Let's see. Let's see. Yes, this is going to be the last question. All right, and this is on page 10 of the eWorkbook, level E questions, and question number 3. In the first few seconds during liftoff, and it's as well we are discussing this now, NASA is just about to, I think there was a problem today, but NASA was about to send its rocket, Artemis I think it's called, to the moon, but there was some issues, so it did not go through. So it's good we are looking at this question because it's related to the sort of thing going on currently. So in the first few seconds during liftoff, a rocket consumes fuel at a rate of 102.71 kilograms every second. So this means kilograms per second. It consumes 102.71 kilograms every second and ejects exhaust fumes, those fumes there, okay, at a constant speed of 2400 meters per second. The rocket experiences a thrust force F, given by F is V times dm over dt. We will say what this means. You shouldn't worry. You should not worry about it. Where V is the exhaust ejection speed. In other words, the speed with which the fuel is being ejected, which we've been given here. And dm by dt is the fuel mass ejection rate, which we've also been given. All right? Use this information to find F and give your answer to the appropriate number of significant figures. So this might sound difficult, but it's really nothing. Okay? Think of this as just one thing. So if we read the question carefully, we are told that that the rocket consumes fuel at a rate of 102.71 kilograms per second and ejects exhaust fumes at a constant speed of 2400, and ejection speed ejects fumes at a speed of that. And down here we can also see it says where V is the exhaust ejection speed. So which this is telling us that V is actually 2400. Okay, that's what that is telling us, that V is 2400. When we look at that there, what I've highlighted there and this, so V is 2400, referring to the speed with which the fumes are ejected. Okay, and dm by dt, the rate at which mass is being consumed. So dm by dt, a rocket consumes fuel at a rate. So this is rate of fuel consumption, 102.71 kilograms per second. So look at that. I'm highlighting that in green now, okay, which is related to that. So fuel consumed at a rate of 102.71 kilograms per second, and it says here dm by dt is the fuel mass ejection rate. So that those two are referring to the same thing. So dm by dt is referring to 102.71, and therefore using this formula here, okay, we know V is 2400 there. And again, I think I've continued to use this, so you can either change that to 2 or change this to, you can keep that as 7 and change this to 7 and multiply by 7 here, 7 1 here, or you can choose to keep this as 2 1 and continue like that. So if we keep 2 1, then I think what I'm going to do is to leave that as 2 1 and make this one here 2. Okay, so it is 0.21. So 102 0.21 there. So if we keep it that way, then it follows that, so we multiply the two. This is to two significant. We are multiplying, so we need significant figures. So this is to two significant figures, and that is to 5 significant figures. All right, look. So the 2400 is to two significant figures. It's a whole number, so whole is right. So because it's a whole number, we start from the right, which means from this side, and we count all the digits, but starting with the first non-zero digit. So we'll start at 4. So 4 and 2, those are two significant figures. This is a decimal number, so we start from the left and count all the digits starting with the first non-zero digit, and you can now see that the first non-zero digit is the 1 itself, and then we count everything, which makes that 5 significant figures. Because we are multiplying, our answer has to be to two significant, the smaller value has to be to two significant figures. So right now our answer is to 6 significant figures, so we have to reduce that so that it is two significant figures. Pause the video and think about how to write that number to two significant figures. Okay, if you've done so, then you should see that the answer is actually 250 newtons. I'm sure if we left this as 0.71 and change this to 0.71, we should still come to 250 newtons. Okay, so I don't think the 7, whether leaving it as 7 or 2, is going to change that figure. Okay, and so this is how we answer this question. It wasn't really difficult. It's just you needed to understand what the question is asking for. It just required us to multiply these two numbers. Okay, so the answer is 250 newtons. I believe that brings us to the end of this video number 5. If you have any question regarding any of the problems from the eWorkbook, remember I just picked a number of the questions. I didn't pick everything. The bulk of the questions are still in the eWorkbook. If there is a particular question you'd like us to go through, don't hesitate to let me know, and I can make another video, or I can go through it separately with you. Okay, if you like the video, please consider sharing it. If you are seeing this for the first time, please subscribe and hit the notification bell so that when a new video comes through, you will be notified. Also, the more you like the videos, you click on the likes, the more it is shared with other students who might need them or who might find them useful. So please continue to like the videos as much as possible, and continue to write comments on the comment section so that I know how well we are doing, and so that I can help you when you face any kind of difficulty. I've started seeing students post questions on the comment section. That's a brilliant thing that you're doing. As you keep doing that, you will continue to improve. Okay, thank you very much. I'll see you in the next video where we move to the next topic.